So some of the early stages of the building us up to some of the background, I kind of was looking at, again, variance partition analysis, the acronym very commonly referred to as VPA. The three words all have, obviously meaning in the English language. Variance by itself is, it's variability. Variance and variability are similar terms. One of the things with VPA is that we're typically looking at a jumbo reel off the paper machine. So that, VPA by itself is a way to take all the information that, for example, the QCS scanner is measuring and quantify that in basically really four numbers, but it kind of comes down to three variability measures. And those three measures of machine direction in two components, and then the CD in another component, are used to kind of give you the ability to quantify the variability of that reel of paper. So that's where the word partition comes from, is that the partitioning is a way to separate the variance or the variability in a way that you can kind of identify a specific area of interest, or where that variability tends to be higher. And analysis is just really, as a word, just the mathematical process, but it is a statistical process that's used. There is some, there can be some differences, but in general, the analysis is really a statistical analysis that's used to calculate the VPA values. Now, when you're looking at the QCS system, whether it's an ABB system or another vendor's QCS system, there are displays and reports, and a lot of those reports and displays do have, for example, like on a profile display where you'll see the word 2 sigma. The 2 sigma value, and we'll kind of get into that in a little more detail here, but it's really a measure of the variability of, say, in this example, it's a profile. That variability, where it's represented or shown in different reports or different displays, what we're focusing on in VPA, though, is really the reel report. So I mentioned earlier what we call like the jumbo reel or the reel of paper off the machine. The area of focus at this talk is kind of going to gear towards is, the reel reports or the VPA variability that's on the reel report. But be aware that there are other there are displays, if you have cross direction or CD control, you're also looking at, separate 2 sigmas, or sometimes the 2 sigma or variability is referred to as a spread, is another term that's used commonly. But that, just be careful when you're looking at a system, you understand, the values that you're looking at, what they're related to. So, it is kind of time-based in the sense of, the variability that we look at on a reel report is at every reel turn up. So we're looking at that jumbo reel and that quantifying that variability. Whether you have grade, like running a grade or a roll set report or a roll set display, there are other variability measures that are there also for you to look at. So again, a little bit of a background, but I think this is a kind of a nice visualization of, obviously the scanner, as the head package is scanning back and forth across the sheet, we're getting one profile, or one, what we call, like you're showing here, a cross direction CD profile. We get one measurement, whether it's weight, moisture, caliper. Each time the sensor head passes, across the sheet, we're getting that profile. So that's, commonly the cross direction or CD portion or the CD profile. In the machine direction, what we're showing here is that as the paper is being produced, each scan will have a scan average that's calculated. So each data point, like in this trend, kind of represents the scan average. So you will notice that that scan average is the MD component, and then the cross direction is each scan. Now, we look at it in another visualization here on the left, showing what we call a contour plot, which hopefully you've seen these, whether it's on a QCS display or some other system that you've collected profiles that you can have this visualization. Where the contour plot is helpful is it allows you to take a look at not only the looks at the data in a color map basically, and the range of the colors give you an idea of what the profile or what the, in this example, for example, we're looking at weight measurement, how that weight measurement changes, over time. Now, the thing here, also the dashed lines represent the real turn-ups. So this actually is probably 10 plus reels of paper that have been produced. So this could be over maybe a 5 to 6 hour period based on the turn-up time. But notice that all the paper being made, the VPA analysis is really focused in one of these rectangular squares, or not square, basically a rectangle. So from dash line to dash line, we're going to have so many profiles that are being measured. And then those profiles are used to calculate our VPA data. Okay. So talking about the terminology a little bit more, scanning, sensors, we have a couple fixed parameters that we have to consider, and we also look at, the CD profile as far as, like I mentioned, that you get a profile, and then you're going to have a scan average for the machine direction that's calculated. These are both going to be related to what we call the sensor scan time. Now that most systems that would be a fixed time, whether it's usually in the 30-second time frame, that scan time is going to help designate, that scan average, for example, is going to be based on that scan time. So it's important to understand the scan time is one component. The other is the profile. The profile itself, we refer to them as data boxes. You may hear them as lanes. We could have, like, if you look at this axis here in the CD, we have basically 1 to 600. So these are the number of data points across the sheet. So across the measured trim, we have these, and actually it might be a little less than the 600 data boxes, and we'll get into that point here in a minute. But if you drew a vertical line up along one of these, what we call data boxes or lanes, that's basically giving you that profile point, along the machine direction. So these number of data boxes are really designated when the system's installed and set up for the scanner. Most of the ABB systems will have a default of 600 data boxes. You may have a system where you have more data boxes based on the type of profiling that's being done, say for a cross direction like a dilution profiler. You may want 12, you might have 1200 or 900 data boxes, but it's important to know that the data boxes also, the number of data boxes will influence the cross direction component of this very VPA analysis. Okay, so that's kind of a little bit of the background. Now that's kind of the background of the QCS system in that regard, but let's take a little step back on the standard deviation and variance and just the variability. So quantifying the data variability, hopefully at some point in your background in schooling, you were introduced to what's called standard deviation. Most everybody kind of has an idea what an average. A data average is very common, that you take a number of data points and calculate an average. But then when you go to sigma or standard deviation, so standard deviation is commonly referred to as sigma, and this Greek symbol that looks like this little circle with the line off the side is the sigma Greek symbol. But just to give you the equation, is you're basically looking at the average, and at each data point, we're looking at how far is each data point deviating from my average, or the mean or the average. So the deviation from the mean or the average is then squared, summed, and then divided by the number of data points, and then taken the square root. So again, the variance or sigma is going to help to measure how much variability is in that data. Okay, so that the variability from average. So if you have data that is very close to the average, then that standard deviation or sigma is going to be a smaller number. But as the data tends to move around and not be close to the average value for the given window of data you're looking at, then that's going to increase that sigma. Now, the variance in itself probably not as common. Some people that you may understand standard deviation, you might not not that you wouldn't understand, it's pretty simple, but the variance is just squaring the sigma. So you take the sigma value and square it. Now, variance by units, and that I didn't really mention it, but sigma on its own, the units of whatever you're measuring, you're using the same units when you're looking at sigma. So if I have like a weight measurement that's in pounds per ream, for example, when I calculate the sigma, that sigma value is also going to be in pounds per ream. So this is a very common, most of all the displays and reports that you would see from a QCS system, everything's reported in a sigma or an X number of sigmas. Very common is 2 sigma. Variance, on the other hand, where it has its advantages, which we'll talk about here in a minute, but as far as the units go, the variance is a little harder to understand in the sense that it's in squared units. So if I'm talking about meters, I'm in meters squared. If I'm in grams of weight, then it's grams squared. So it's a squared unit. So that makes it a little more difficult for the end user or whoever's looking at the data to relate to the quantity, because it is a squared unit. But it does have its advantages, which we'll show here in a minute. Carrying on with the statistical part of it, distribution. Now, the distribution we're showing here is a normal, what's called a bell curve. And we like, from the statistics perspective, if you have data that is distributed, normally it's going to allow you to do these the amount of data like in 1 sigma. So plus or minus 1 sigma, 68.3% of my data is going to fall within this plus or minus 1 sigma. This is important to understand because for normally distributed data, we can make these estimates or these values hold. Now, not all data is normally distributed. So that, it's one of the important aspects is that just because you have data that is not normally distributed doesn't mean you can't calculate a standard deviation. You can still calculate it, but it does mean that these percentages don't hold. If you have data that's not normally distributed, then these 68, 95, 99.7% ranges don't really hold anymore for that. And that is something important to understand because there are times when in paper making we're calculating 2 sigmas based on data that's not normally distributed. Okay. Moving on to, we're going to do kind of some examples here, and this is kind of that was kind of the end of the introduction part of it, and we will talk about a little bit more specifics of the VPA and some of the relationships, and we really haven't introduced the 3 components in detail yet, but that's really kind of the background of the statistics part of it. What we're showing here is just 2 examples of, now this data, like I mentioned earlier, these are scan averages for close to say 300 scans of data. If you look at these occurrences, like if I look at the range of say 32.5 to around 33.5 or 34.35, so it's probably about a tenth of a pound per ream. This range, you can look at the value. So as the value repeats, that's for that histogram. So this is kind of just like the plot we were looking at before. We just took it and we rotated it 90 degrees, and we're showing the number of occurrences of each of these data points in, sometimes they're referred to as bins, as a histogram. If you look up or if you have any background on what a histogram is, this probably makes a lot of sense. But with the histogram, it gives us, at closer to the average, we'll see data, if we have data that's normally distributed, we'll have more frequent values closer to the average. So it is important to, kind of have an understanding of this. Now, this data being the MD component, or the scan average, we have, for example, a sigma and a variance that are calculated. Now, at the same time, we can also look at this one being the average profile. And we'll get into a little bit what we mean by average profile here in a minute. But thinking of an average profile of a whole reel of paper, we're going to then, again, we're going to look at the statistics and do the same histogram, but now this is the CD component that we're looking at. So we're looking at the CD sigma and the CD variance. Okay, so kind of moving on here, let's get into a little, this kind of drives us into the VPA component a little bit more. So up to this point, we've been really talking about, kind of the background, and now we're going to kind of break out into the three components of VPA, or sometimes I say as four because you have the total, but the total is really dependent on the three individual VPA values. So the three values we're going to discuss are MDL, which is the machine direction long term, the cross direction, which the CD component, and then this one. Now this is named, I think on the ABB systems, you may see it called residual, or you might see it called MDS. I think traditionally in history, we refer to it as MDS quite a bit, but then also as residual. Everybody has kind of their personal preference, but they basically mean the same thing, but it can be a little confusing as to, it's really the remaining variability of what's not in the MDL and what's not in the CD calculation is where we're trying to say that residual or MDS component resides. Now, looking at the summation, now this is another really important point, is that the values of MDL, CD, and MDS or residual, those are typically shown on, say, a real report as 2 sigma values. If you take the 2 sigma values and you add those together, they don't equal the 2 sigma for the total. You have to add those in variance units. So that's usually one of the, somebody that just starts working with the VPA data or looking at the real report, that's one of the early things that they'll try to do is add the 3 values together and then ask why the total is not equal to those 3 values. So all you need to do basically is if it's in square the values to take those as variance, then you add them together and then square that total that you have for 2 sigma, and then that will be. So the X and sigma, that value is, most systems are 2. There are some systems, at least for the ABB QCS systems, will have customers that will do 3 sigma instead of 2 sigma. So that is something you want to check, on your particular system. You want to verify what sigma value is being represented in the reports. This area is something maybe that some of you haven't really been exposed to. If you know VPA or you look at VPA data, one of the areas that we like to consider is how to break those, the scan itself for a whole reel build, how long it takes to build the reel. We're breaking out those 3 components. So the machine direction long variability, that variability as far as the type of variation that's going to be composed in that MDL value, we estimate that between the time to make 2 scans to the full reel build time. So that's one important thing is that the MDL is limited to the build of the reel. So like if you're looking at a reel build and say your average reel build time is like 45 minutes and you have a frequency that's like 3 hours that you're trying to look at, you may not necessarily see as much of that in the MDL on the VPA report. You'd need a longer set of data to look at it. Now, staying with the machine direction or MDL, let's go to the residual. The other side of that is that the time, so MDS, and that's where the machine direction kind of gets grayed in a little bit with residual, but residual doesn't necessarily mean MD only, and that's, I'll kind of point that out in one of the examples too, but it's really this variability, and we estimate that is the time to make 2 data boxes to 2 scans. What do we mean by time? Well, time in the sense of MD is variation that is time-based or temporal-based. So residual or MDS, the time to build 2 data boxes, for example, on a 600 data box scanner where you're measuring close to 600 data boxes and you're at a 30-second scan time, you actually will get variability that you can see as fast as 10 hertz or 10 times a second. up to the time to build 2 scans, which if you're doing a 30-second scan time, that would be up to 60 seconds or 1 minute. So the range of the MDS, again, is going to be in the range of, say, 0.1 seconds or 10 hertz to as slow as 1 minute. Now, when we talk about CD, the variation that we can see in that CD profile is the width of 2 data boxes to the width of the reel, in the sense of what your trim. This is really your trim. Now, notice here we're talking about variation, but it's width and it's spatial. So we're looking at distance. Here we're talking time base. Here we're talking distance. A couple other important factors. Excuse me. Let me grab a quick drink here before I apologize for that. Some of the base factors that, and this is an important aspect, is that thinking about how the, VPA, the variability that you're measuring on a given, whether it's weight, moisture caliper, obviously there's process factors that are going to influence that variability. But in addition to that, there are some base inputs or base factors of how the VPA data is calculated. And we already did talk about the scan time, number of data boxes. And then there is a slight difference between the maximum. That's why we typically set up a scanner, and we want to maximize the scanner as far as how it's set up for the maximum trim that we're measuring pretty close to that. Also the real build time, and then the trim width itself. So these are all factors that are going to influence the VPA data, in addition to your process behavior, and then also the sensors themselves. We'll talk about that too a little bit, as far as the sensor alignment, and then also the sensor maintenance is a critical factor also for the VPA data. Okay, I didn't. We'll try to. As you saw, I think the time wise we're running for an hour here, so I'll try to leave a little bit, probably about 5 minutes here, 5 to 10 minutes at the end, so we can have some time to answer some of the chat questions. So as I see some of those have kind of populated in here, and I'll kind of go through those as we get closer to the end. As far as VPA goes, the TAPPI, there are 2 TAPPI methods, and there's actually been some recent work to redo some of these TAPPI standards, as far, not redo, but rewriting. I know like the T1101 had some recent updates to it also, but there's a T545 and T1101. And if you've never looked at these, I would recommend you go get on the TAPPI website, and you can request for pretty much a minimal fee. You can get both of these technical standards from TAPPI. And these, I'm not going to go into these in real detail, but just to kind of mention that there are 2 that you can get some information on. They both methods actually do calculate the VPA values, but they're both kind of designed for, the origination of where they came from is a little different. The T1101 was really for not as many samples, and like if you had strips of paper off the machine, you're running them through the lab, and you're coming up pretty easily with an Excel worksheet or a spreadsheet. You could fill it in and give you a quick calculation of the VPA values. The 545 method is statistically a little bit more in depth, but at the same time, it's using a lot more. Normally it's using more data, as far as like what, as we mentioned, the scanner itself has 600 data boxes, for example, 30-second scan. Say if you're doing like a 45-minute real build, you're going to have 90 profiles that you're going to get during that time. So there's a lot of data that's being analyzed. So just be aware that those 2 methods exist, and those are referenced. And typically the T545 is probably statistically closer to what the ABB VPA does. The VPA in the ABB system is calculated during each scan, updates, but then it actually gives you the final values at real turn up. Now we're going to continue on with some examples. For this example, what I'm going to discuss is, again, we're back to the contour plot. And with the contour plot, we have each scan. So going vertically, we're going in the machine direction. So the sheet, you could think of it running from top to bottom. And as we're scanning back and forth, we create these profiles. Now, the MD as the scan average, this MD scan average, each profile that's measured, we're getting that scan average. Now, when we talk about the average of this data, this is like the average of all the scan averages. So that's what this value represents. Now in the cross direction, we're looking at a given lane. So as the MD scan average, we look at the average across the profile. For the CD average, we're looking at a data box or a data lane. In that data lane, for example, in 100, we go vertically up. We're looking at all that data, and that's what we get the value here as the average. So the average profile is taking the average of all of those profile, or not profile, but the data lane values. So in this example, if we have a real build, approximately 50 minutes, scan time of 30 seconds, 600 data boxes, and we're measuring, say, 559 data boxes, this is a number of points. So you've got 570, 57,000, actually more than 57,000 data points. Now, one of the things at this point you're kind of thinking in your mind is like, well, I've got 3 values of variability that I'm measuring and using, but I've got over 57,000 pieces of data. So it is kind of a data compression in that sense, that it is, and this is one of the things you'll hear is people will say, well, I don't really like the VPA data calculation because it compresses the data so much. I lose sight of what's even happening. And that, in some ways, that is a true statement, but at the same time, it is important to understand that the VPA is a wealth of information. And Lee Barber, which was one of the guys that was kind of in ABB when I started at the company over 30 years ago, really helped me and really probably helped Kevin, I know for sure, as far as understanding what the value of the what VPA data value is. So I think, to ignore it and not look at it is we are missing something. So it does give you that first step. And that's where we're kind of drill into here a little bit more as we move on. Okay, so we're at a point where we've got the scan averages, and then if we take the variability, now we're looking at, if we have that trend of the scan averages, and that's where the MDL kind of comes from, is we're looking at the variability of the scan average. We're also looking at the variability of that average profile. That's where the CD component comes from. And we'll talk about the total, but the total is looking at the variability of this entire contour plot. So it includes the MDL, the CD, and also this MDS. And we'll spend a little bit more time on that as we move into this next part. And at this point, what I was going to do is kind of hand it over. And Kevin's been quiet. I probably haven't given you a chance to talk yet, but this is probably.
Well, I've been typing on the side, so I was your comment window on the side.
Oh, okay,
so
that's good.
I was adding the rest of the story.
If I've said anything totally incorrectly,
No. It was great. I mean, there's a lot of, as I'm listening, there's a lot of statistics in here, and we can sometimes get overwhelmed with all the math, and we're like, oh my goodness, I'll never know all this. And literally, statistics are a measure of variability. It's an indicator, and that's where Lee would always say, and Kevin, you need to learn how to read this. There's gold in this data, and the troubleshooting techniques between variability sources. We'll get calls, hey, my real build variability is just too high. Okay, well, that's total usually. Well, is it MDL? Is it MDS? Is it CD? There's 3 different lanes that you can try, and they're very, very different, whether you're doing it. And that's what we're going to show next. But if I've ever been with you in a site, I'll draw this picture almost, a lot of folks used to, VPA is one of those things, is when it printed out on a deck writer, there'd be a wall of paper on 11 by 14 sheets. And I mean, go back to when I first started, Tim and I have been around a long time, is I'd have to, back to, I think it was Lotus 1, 2, 3 or Symphony, we'd have to be entering in all these variables and then trying to calculate a histogram. It took hours. Now it's right at our fingertips, yet there's so much data, it's hard to be able to see, well, where it is the data. And so I'll just draw this picture. So what I've got here is I'm trying to, in your mind, imagine a profile. So the top picture, the top line up there is a profile, and we call it, it's got a zigzag, up, down, up, down. Every other data box is up, down, up, down, up, down. And then the next row is another profile. And that's one difference about the way we think in scans. A scan for ABB sensors are from one side of the sheet to the other, and then we traverse back. So we don't average forward and reverse scans. Our frames are pretty tight, and so we can actually measure each direction. So this one, you go one direction, it's up, down, you come back, it's up, down, the opposite. And so if you look at that, every other scan, it flip-flops. And every other data box flip-flops. So visually, just looking at this grid, you would expect there to be a lot of variability. But I just happened to set it up so that if I average each scan, this scan average is the same. So there is no variability in the scan average. And then if you average every data box, it's flat, so there's no variability in the profile. So that's the thing, is if your real paper looked like this, please call us. You got something really bad happening. But from a visual interpretation, you can see that the MD and the CD averaged to 0, yet there's a lot of variability. That variability is what we call MDS. That's the residual. It's just the stuff that's left over in the sheet that gets washed out in the average. So the way we like to think of is your MDL and your CD are kind of your persistent patterns that are there in the average profile. Your MDS is how the data moves around those averages. And when we're troubleshooting, we really like to very quickly take that picture. And in today's world, you can have residual profiles. And I think Tim's going to show you some examples of that. But I can remember being one of ABB's early firemen. Is I'd get called into the mill, and I'd always try to walk in towards the dry end. I'd go to the lab and find the 8.5 by 11 or 11 by 14 sheet of paper, and I'd be reading the real reports for weight, moisture, caliper, size, and just as I'm walking into the gauntlet, which is the office where the mill's down, and they're like, "You're causing us issues," and I've got myself a battle plan. From the back of the machine to the front of the machine, said, okay, your problem is in moisture, machine direction, we're going to do bump tests, and we're going to fix this. And it is remarkable is how fast you can look like you know what you're doing if you can interpret this data. And that's what we really wanted to convey here, is there are ways to do that. And that's what we'll show you at the end are some promotional items for you being here. But you can go look at your real reports right now. And I hope all of you will look at them in a little different light. But now with the strength of the contour plots, which is unique to our paper industry, is we can actually see the sheet. And so, Tim, I think you've got some real examples that you can show next.
Yeah, no, that's great. Thanks, Kevin. You can kind of interject as we're going through here if you have any comments. So this, taking what Kevin was just talking about and then throwing that as, and this is actually an example of where this data actually is the residual. So you can calculate the residual by removing the scan average and removing the average profile. So you'll notice this data set has the CD and the MDL component are effectively 0. The MDS is, and there, I will tell you that, and I've still even working with engineers over the years that, they'll treat the MDS or the residual as something to ignore. I'm a proponent, and I would highly recommend that if you've ignored residual or MDS in the past, you start to look at it more closely, and hopefully you'll kind of understand why we're saying that as we kind of go through. One component, and again, we don't necessarily want this to happen, but this is one of the side effects that can occur. Is this, again, as Kevin, this kind of shows it a little bit kind of a data path in the sense that each profile is alternating, like Kevin was showing in his original, in the previous slide where we had the example. You'll notice again, just kind of shows you the way. And if you think of the scanner, if you have like a head alignment or some issue with the scanner where it's kind of flipping from forward to reverse scan and causing some issue, that it really will show up in the MDS, where it may not show up in the MDL or the CD component of the variability. So that, and it's not, don't get me wrong, it's not just the scanner that is the contributor to MDS. It's process too. Your process can contribute to the MDS. that's one of the other things I think that are important too to consider or to realize. Okay, at this point, I think Chris is we're gonna do a poll question here, and hopefully he can pull that up. I don't know if I can really see it from my side, but kind of read through here, and then you can go ahead and answer the poll question for like your basis weight sensor.
Okay, should be seeing the poll. We've got about a minute for this.
So all we're looking for here, and you could, you know, for basis weight, which is, you know, basis weight, dry weight, you know, for your particular machine, or you can pick a machine that you work with frequently, where the issues typically lie.
30 seconds.
Need a little background music for this part.
We can say we need Jeopardy to play here.
Roy Coleman would always have some background music.
Crickets. We should have crickets chirping.
All right, just finishing up a couple here, and give me a moment, and I'll publish the results.
Perfect. Thanks, Chris.
Yeah, it's not like there's a wrong answer here. It's your machine. You may not know. We should have had it's okay. A lot of customers don't, you know, and that's what we're trying to, I hate to say we're bringing VPA back, but this is really powerful information, and it can lead you. And I think that's the next section is going to be how to sort of take this. So yeah, a lot of folks didn't really know, but profiles, so that's interesting. So that's where what we would do is, like, if we did, this would be something we would do, and we'd look at your numbers and we say, oh, CD. So in this case, if you were a customer that had a profile problem, then we're not going to be talking to you about doing bump tests on your MD controls. You're now so we can isolate our swim lane for troubleshooting. All right.
Yep. Thanks. Okay, so Kevin kind of alluded to this a little bit earlier, and this is also from the beginning, is VPA the end of the story? And I think that's one of the areas I can tell you that from working in the optimization services group for the past 10 plus years, that, you know, is an area of looking at further, you know, the VPA data is a great place to start, but it's definitely not the end of the story. So why we say that, you know, cross direction, there's a lot more, you know, you're going to, you know, I should have mentioned that earlier, is that the VPA data, the data source for that is what we call the raw profile. Now, not necessarily raw in the sense of the electrical signal from the sensor head, but raw in the sense that it's the unfiltered profile that the QCS creates, you know, at an unfiltered level. It's not the profile, for example, that's used for the cross direction control, or say the MD control, what it uses, but that profile is what's used to generate these variability values. So if I have, for example, a cross direction issue that I'm trying to, if I have elevated CD, you know, the raw profiles I'll be looking at. I'll be looking at the actuator set points of the CD actuators, spectral analysis and CD bump tests. Definitely areas to, you know, further investigation. The MDL, or the long-term MD, this portion, you know, we're typically in the, you know, not always PID, but there are PID loops that definitely can affect this. Machine direction loops, you know, for the QCS. So we're looking at spectral analysis of MD and DCS loops. The MDS, or the short term, some of the sources, like I mentioned, 600 data boxes, 30-second scan, you know, it's 10 up to 10, as fast as 10 hertz actually is variability that you can see. Now, it is important. I've got another example here to kind of get your mindset on that. But, you know, we'll look at, say, single point high-speed data collection. We also, MDS is this residual profile. The residual profiles, and remember what we meant by residual profile is you take the profiles, the raw profiles, and you remove the scan average, you remove the profile average of those set of raw profiles, and that gives you what we call the residual profiles. And that will actually help you to visually see some things that you may not have seen just by looking at the raw profiles themselves. Now, this you may have, there's similar versions of this kind of display, but that, I think I did see one of the chat questions pop up in regards to comparing machines and, you know, when you're looking at VPA data from machine to machine. This is, um, this is an area that can be challenging, but there are some basic things to look at. One is the data boxes or data lanes, the scan time, and then the real build time. For this example, we use the same real build time, but a slightly, you know, double the scan time and then much less data boxes. You will see that the 60-minute real build time kind of is one boundary. You'll notice that the MDL breakpoint, you know, it's 1 minute to 2 minute between the two machines. The residual is quite a bit different. You know, say if you've got, you know, the residual on the 60 data, and that's, you know, one thing you'll say is, well, I don't have any machines that do 60 data boxes, but I will say that there's some I've seen even recently that do 120 for VPA. Now that's the our key is that for VPA. VPA, at least in the ABB QCS, you can map the VPA calculation to something less than the 600 data boxes. So if that's something that you're not sure of what your VPA data is being calculated, I would recommend that you go figure that out. And, you know, the way to do that is you can work with, you know, whether your ABB field service representative is or whoever your contact person is with ABB. I'd reach out to them and ask them, hey, how do we calculate VPA on our machine? You know, what's the number of data boxes that are used for the VPA calculation? The reason I bring that up is that residual. Now, maybe you don't want to see it, you know, but I hopefully you do, because if you do have some machine characteristics or process variability that you can see in the VPA MDS that you may not be seeing with something that's mapped down. So here it's between a half a hertz to 10 hertz is the breakpoint difference between these two examples. So we also kind of show the decades here in the temporal portion or the time base. So each of the decades as a cycle, if you think of, you know, the MD cycles that are occurring, kind of each of those 6 decades where some of these areas fall, you know, and these aren't hard limits by any, they're just kind of approximations, but just to kind of give you an idea of where those areas are. And then also the CD is separate in the spatial side. The limits and that portion, I wanted to kind of just bring this topic up. The goals and the limit criteria. We kind of refer to goals and limits. What we mean by a goal is that the goal of VPA is to get to these goals of, we have like a 70-20, 10% in the variance distribution. So again, we look at the variance distribution as a percentage. Then we also look at that distribution, the total. So the goal as far as a total, like for example, as a percent of process, and this is something I didn't talk about yet, but typically, as I mentioned earlier, the 2 sigma could be in or in pounds per ream, for example. It's in units of the sensor. But for some sensors like weight and caliper, we usually will do those as percent of process. The reason we do as percent of process is to try to allow that measure to be more meaningful when I look at like a heavyweight versus a lightweight grade. So that 1.5% versus the 1%, these are the totals. So those total values, and then based on these distributions, these will be our goals. Now, what are the limits? The limits are values that are typically going to be higher than those goals, and those may be for a particular machine. So your machine, if you pick one where it runs well or where you feel you're at, that's kind of where it nominally runs. So that's what we call the limits. Now, I'm going to kind of change gears here a little bit and just jump into some examples, and hopefully you'll see some of the value. And this brings up a couple other points of interest or points to talk about, is that for this example, this is showing an elevated MDL. Now, each one of these plots, there's a lot of data here, and that's one thing you will see is, if you remember, I talked about normally distributed data. Now, remember, each purple or magenta value is actually a reel of paper. So there's a lot of, this is actually like a year's worth of data. So over a year, all the MDL values for moisture, for basis weight, and dry weight are all plotted. Here we can show that there's an elevated MDL that occurred around in the September timeframe. This one actually, the black circles are the daily average. Because the MDL typically is, it's definitely not normally distributed as far as when you look from reel to reel. That's kind of one of the tricky things with VPA, is that we look at the history of VPA data, and then we start talking about statistics of the statistics. And that is something that you have to digest a little bit. But, here I'm talking about the MDL is normally distributed, but it's over a year of data. But the VPA values themselves, the black circle is the daily average. So the daily average really helps us to see, the trend of the daily average. The other thing that's important here is that we tend to, when we look at long-term data for VPA over, more than a day, we're looking at typically a median and not a mean. And that brings up another, why do we do that? Well, because we know that the MDL, for example, is not normally distributed, a median actually gives you a better approximation of where the steady state or where that guy runs. Okay, so this example just shows how it was elevated, and the correction here, it's actually $250,000 of savings if they can get that MDL back to where it needs to be. Okay. The next one, this is one I think is really a neat example, is the MDS is what we're showing is elevated. Now this plot, this is actually off of one of our service ports at a site here in the US, that where we look at, it's interesting because this period, it's probably a couple reels of paper that we took the actual raw profile. So this plot is off the service port, and it actually shows the CD and the MDL and the MDS plotted. So each data point again is a real paper. This is like from 1 quarter or like 90 days. So that collection period, you can see the elevation of the MDS is really what's showing up in this. See this kind of a spiral pattern. One of the things you'll say is, well, CD, you typically jump right on mapping. This one actually was over control. There was over control on a re-wet or air water spray, and that over control is actually causing the CD actuators to oscillate in the MD direction. And I know that there's a lot to digest, but basically if you think about that, you're, where a mapping issue, you get kind of this what they call barbershop pole or spiral pattern. You're also getting it, but this is more from over control. The key to this, though, is that if I was only monitoring the CD and the MDL, I would have missed this. Now, obviously, you're saying to yourself, well, I'm not going to miss that. I'd see it in the contour plot. But at the same time, I can tell you this can get overlooked. And this is where the MDS actually helped indicate or show that. So this is another example. And here we actually did the tuning update on the re-wet and got that corrected. Here's another example of, and this is off of one of our ability platforms. And on the ability platform, it's a similar plot. I kind of, instead of the black dots, we have white dots to represent the daily average. These are the actuals here. So the dry weight actual, but you'll notice that the CD component increased. And as it increased, we have a KPI that kind of gives us an indication as this is above our nominal where our limit is. So the limit is now remember I talked about a goal and a limit. The limit is kind of where the machine runs. So the limit helps us to understand when we're above the limit, we're going to start accumulating. So I can look at the data and see it, but I also can look at this where if the values are sitting at 0, I'm doing well, versus it starts to ramp up, that means that I've got variability that now is increased. So this one was related to dilution, a dilution head box. It just the flush cycle itself needed to be done. The site really wasn't running it on they needed a PM kind of set up to run it on a more continuous basis. Not continuous, but just to get it scheduled, because it ended up being related really to the flush cycle there on that one. To kind of wrap it up, and we do have, I know we're down to the 5 minutes on the hour, so what I would like to do here is just kind of talk about the benchmark and what a benchmark is. And as a quick example, we typically look at about 3 to 6 months of data. We also would focus on weight, moisture caliper. Now, obviously, VPA is calculated for all the sensors that the scanner has, all your like your optical sensors, your ash. And those sensors, not that it's not, it could be important, but for our benchmark, and this is usually your initial focus. Initially, you're focused on weight moisture caliper. The data source doesn't necessarily have to be our ABB QCS. We can, as long as you have, a QCS that's calculating some type of VPA values, we typically can take those. And they may be in a mill historian, they may be with the OPC data collection, but there's some data source for those. And then the benefit is really, hopefully you see the benefit. The benefit is really what we've been kind of showing, is that understanding, again, where you are versus the goal, where your trends kind of go. That's why we look at 3 to 6 months of data to look at, are there potential step outs or anything that occurred. And it's really provides opportunities for talking points for potential improvements, or the pretty important part of it. So with that, I'm going to kind of move on to the last set of poll questions here. And this one, again, has a lot of options. So we're looking for any input. And with this, I'll try to kind of read through as you're answering these, I'll read through the chat window here. And I don't know.
Chris can go ahead and put those up now. Yeah, there you go.
Yep. I guess
can you go read through them? Can you hear me?
Yeah, I can hear you, Kevin. Yep.
What I was going to say is, like, what you have here is you can click boxes down the right hand side, and Tim and I have written papers for TAPPI on this subject. And if you click that box, we'll make sure that you get them, because when you logged in, we'll have your email. We actually have some YouTube videos that we have done that you could watch this, and we'll be putting this one out as a YouTube video as well. We want you to know this information because it can dramatically reduce your troubleshooting steps. For you listening today and for you logging in, we're offering a promotion. And we're going to cap it at 25. We're learning through these webinars. Is if you're interested, you can give us a check this box, the VPA benchmark. And what that will do is we'll trigger an email to you that will define the data source and format, and we'll work with you. But we love doing this analysis, and we feel that if we can help you make more paper, that ultimately you'll come to ABB to buy more stuff. But we want you to make better paper, especially right now where the industry and the whole world's kind of in a mess. We're finding that when some of our customers have had to throttle back and they're having issues that they're not used to seeing, the VPA data would really help us. We could show you a snapshot in time from maybe when you're running at the full speed and now, and tell you, and you may need to adjust your tuning or setup for the parameters that you're running. And we have some customers that are having to run so fast they can't hardly catch up because of demand. So either way, we can help identify the sweet spot as a first pass. So this is something we're offering. Just click the button. Now, the next three check boxes are services that we feel go with this one. And again, we want to be able to provide a discount, especially now that we can do a lot more things remotely and digitally. The paper machine fingerprint, we actually invented, I don't know how long it's been now, Tim, 15, 20 years ago. And VPA was part of that, or it is part of that. That's where we started learning so much about it, and we've written a series of analytics around those. But the paper machine fingerprint was really help identify problems, values, and recommendations.
I'll pull up the last slide after this one. We end. I've got some references there that everybody.
Okay. The extended advisor, that one trend that Tim showed, you can actually get that on an iOS device or a computer. It's not we're actually getting ready to it's being released. So if you're interested in that, a lot of our clients are wanting performance accelerators where we can actually, instead of going to looking for an issue, when the issue happens, it tells you. So the email fills your box on problems that are aligned to your site. We call those performance accelerators. And then if you're interested in just consulting with us, these 4 areas at the bottom, we tried to capture all of our I don't know how many products we have into the ones that we felt would complement this discussion. So we're doing more digital QCS supervisory loop tuning where, customers are working with us because we can't come to site. We can work with you through some of the remote capabilities. The CD checkup for you folks that mentioned you're having CD problems. And you like some of the higher level resolution, the CD checkup, we could go right there, and that's incredible service. for some of you that had the MDS or the residual issues, I usually will ask folks if they're having lab correlation issues where the changes, they go in one spot, they move over 6 inches and it's different. You need high-speed analysis. We can help you with that, or training and coaching. So I guess, Chris, did you get enough check boxes there?
Yeah, we're good. We do have a couple questions I can read off here.
Why don't you go to the last one real quick, and so they can look at the reference material, and then we'll.
Yeah, I'll change that.
Way, I know we're at the top of the hour, and so,
Yep.
so Tim can.
First question is, does ABB use a custom method other than the TAPPI 1101 and T545 standards?
Yeah, no, I can. It's not exact to the. And I can be like I wasn't involved myself in the coding of it, so I can tell you just from my background, I know it's closest to the 545. I don't necessarily know if it matches it exactly, but it's close to that. So it's not custom. It's not designed to be custom, but I think it's in the nature of online measurement that how it's done.
I believe it's as the number of scans builds in the reel, they converge. We had some.
I know between the 1101 and the 545, statistically they become not really any different with more data, but when it comes to the actual calculation that's used by each vendor, but it's not custom, it's closest to the 545.
And then one more here. It says, is there a best practice for using VPA to compare performance of a number of different mills/machines?
There's a couple. There's a central value theorem. There's a bunch of. That's a great question, and we get asked that a lot. And we actually do have a fleet analytics that we can apply. If you remember when Tim showed, you could actually make an argument that it's no. If you have different sensors, different spot size, different data boxes, different trim, different scan time, your inputs to the VPA data is all different. Having said that, we do it all the time. You have to kind of look at it through a little different lens. But when I'm thinking of some sites that had like 6 machines all running together, and we would perform this analysis on all 6, and man, it showed everything. So statistically speaking, it's very difficult to do what the reader is asking, but practically speaking, you can use that to identify problems and outliers and where to look. Tim, you can probably make that sound better.
Yeah, I would. And over the years, I think there's some rules of thumb that we've kind of come up to try, but there's not really an exact method to go from one machine to the next when there are differences. But I think if you're trying to split hairs, yeah, they're different. And but at the same time, there are ways to do the comparison, but you do have to be careful. We
run into, Tim and I have been around when there was 60 data boxes, and then they went to 600 and 1500, and there was a lot of, if you can get the raw data, you can get a little closer if you map back to a common number of points. It's still not exact, but it gets a little better, but then you're not using the raw VPA data. You're using the raw data and add analytics to get to something. So we tend to try to do it as easy as we can to look for relatives in the MDL MDS CD calculation so we can know where to troubleshoot, because that is correct. Anything else?
That's all we have.
Well, we are just a few minutes over, folks. We really thank you, Tim. It was wonderful here, and it's kind of amazing the road and the journey we've been on. I think Lee would be very proud. He's the one that said, Kevin, there's gold in this number. I was a little BYE, bright young engineer, and I just throw those stupid real reports away. And he said, Kevin, you need to learn to read those. There's gold in these numbers. And he's right. Yep. He's right. And I hope that we're a company, you're a company. We want you to make the best product possible because we'd like you to buy stuff from us to help do that. Thanks, Neil. You are correct. I got some private messages coming into me about Lee. It's great that he had such an impact on so many of us. It really was. You're just amazing. I feel so fortunate to have been touched by these great analysts, and the one with Tim and Pete and the whole crew. So we're here to help. We love doing this stuff. And the VPA fingerprint or benchmark is a pretty easy way for you to work with us or us to work with you. And these papers, just if you check the box, we'll get back with you. And we look forward to the next Tech Talk, guys.
Yep. Yeah. Appreciate everybody listening in. Thanks for all your help, Kevin
All righty,
and
guys.
Chris.
Tim and Kevin, thank you. Well
everyone.
done.
Thanks.
Everyone, that concludes our session. Have a great day.